welcome to this explainer of the source material. Today, we're diving into something seriously fascinating. We're taking a journey right through the research, moving from basic, fundamental material properties all the way up to advanced real-world structural simulations. Specifically, we're looking at exactly how engineers evaluate, design, and simulate anisotropic composite materials and structures based on some pretty complex strength and stiffness criteria. If you've ever wondered how modern aerospace components manage to be incredibly lightweight, yet astonishingly strong, well, you are in exactly the right place. Let's get into it.
So let's kick things off with a crucial question, one that really frames everything we do in modern structural engineering. Why don't advanced composites fail like traditional metals? You know, if you grab a piece of steel and bend it, you generally know exactly how it's going to yield. But with advanced composite structures, we're dealing with a totally different set of physical rules. They possess this unique, highly directional strength that requires a completely different approach to evaluate and simulate.
Okay, let's dive right into our roadmap for today. First, we'll look at the anatomy of anisotropic composites. Second, evaluating strength and stiffness. Third, predicting failure in composites. Fourth, designing via finite elements. And finally, simulating dynamic aerodynamic loads.
Starting off with Section 1, Anatomy of Anisotropic Composites at the micro level.
To really wrap our heads around how a massive composite wing or hull behaves, we actually have to zoom way in to the absolute micro level and look at just a single layer of material. Notice how these layers of composite material are stacked on top of each other, but the fibers in each layer are angled differently. You've got 0 degrees, 90 degrees, positive theta, negative theta. It's kind of like the grain in a piece of wood. Just as it's way harder to chop wood against the grain rather than along it, these composite layers have a directional strength based entirely on those fiber angles. By stacking these off-axis layers, engineers can essentially program the strength of the material in very specific directions.
And this brings us to a really fundamental definition. The metals we've used for centuries, stuff like steel or aluminum, they're generally isotropic, meaning they have identical properties no matter which direction you pull them. But the composites we just looked at, those are anisotropic. They exhibit distinct mechanical properties depending entirely on the direction of the applied force. This crucial difference is exactly why we need completely different mathematical rules and stiffness criteria to evaluate them.
Moving right along to Section 2, Evaluating Strength and Stiffness at the meso level.
All right, so scaling up a bit from those microscopic layers to the meso level, we need to look at how the whole plate acts under pressure when it's bent or twisted. To mathematically predict how a composite plate will stretch or warp without getting totally lost in dense tensor equations, engineers rely on specific stiffness matrices derived from Hooke's law. We've got the membrane matrix, which we call A, the coupling matrix B, and the bending matrix D. Now, because our material is anisotropic, stretching the plate might actually cause it to twist, and bending it might cause it to stretch. It's wild, right? But these A, B, and D matrices allow us to calculate those complex interactions perfectly, mapping out the effective stiffness of the entire stack structure.
Which leads us directly into Section 3, Predicting Failure in Composites.
Once we understand a structure's stiffness, we face our most vital engineering challenge, determining exactly when, where, and how our carefully designed structure is actually going to break. We evaluate those material limits using different failure theories, and it all depends on the complexity of the stress. Now, for traditional metals, failure criteria are fairly straightforward. But here, we've got options. Maximum stress is great for quick checks along the principal axes. But for anisotropic composites, we often rely on the Tighe-Hill theory because it accounts for the interactions between stresses in different directions. And for the really complex, multi-axis stress states, say where a material behaves differently in tension than it does in compression, we use the Tai-Wu tensor failure criteria. Ultimately, this is how we push the absolute limits of design while staying safe.
And make no mistake, this math is literally high stakes. As the source material points out, predicting damage in laminated composite aircraft components due to impact events is an area of ongoing research to reduce certification costs. Think about it. Whether it's runway debris, a sudden hailstorm, or a bird strike, mastering these failure criteria is what actually prevents an aircraft component from snapping mid-flight. Accurate predictions save time, they save money, and most importantly, they save lives.
All right, Section 4, Designing via Finite Elements, or FEM. So, you might be wondering, how do we actually apply those strength and stiffness criteria to a massively complex shape like an airplane wing? We move to computational design.
We can break this incredibly dense finite element method down into a pretty digestible 4-step procedure. First, we model the composite layers. We often use the Mainland first-order shear plate theory here to accurately capture how the layers slide slightly against each other. Second, we formulate the global stiffness and mass matrices, basically aggregating all those A, B, and D matrices we talked about earlier. Third, we apply our boundary conditions and any external loads. And finally, the computer solves this vast system of equations to find exact displacements and stress fields across the entire structure.
And this brilliantly illustrates how the computer literally sees the structure. It takes an infinitely complex, continuous physical object and just chops it into thousands of tiny mathematically solvable pieces called nodes. By calculating the exact stress at each individual node, we can accurately predict the behavior of the entire macrostructure.
Finally, Section 5, simulating dynamic aerodynamic loads at the macro level.
Okay, let's zoom all the way out to our fully designed structures. Here, we hit the absolute cutting-edge part of the source material to see how these things behave under real-world, chaotic physical forces, like wind. Researchers aren't just simulating static loads anymore. They're simulating dynamic aerodynamic loads on smart composites. Specifically, they're analyzing composite plates reinforced with stiffeners, or ribs, that are embedded with piezoelectric layers. They subject these models to aerodynamic loads using Scanlon's model to evaluate dynamic stability and find the exact limits of aeroelastic flutter. Now here's the crazy part. When the plate starts vibrating dangerously in the wind, those piezoelectric smart layers can actively generate an electrical field to dampen the vibration and control the structure in real time. It is essentially a material that fights back against the wind.
Now, predicting this involves some highly complex, nonlinear dynamic responses, often calculated using what's known as Newmark integration. But, as you can imagine, you can't just blindly trust the math when you're building aircraft. The ultimate test is comparing that theoretical FM simulation directly against physical wind tunnel testing. Researchers actually build the physical models, outfit them with strain gauges and electrical sensors, and blast them in a wind tunnel to ensure the simulated data perfectly matches physical reality. This rigorous check is what guarantees total reliability in the final design.
So we've gone from the microscopic angle of a single fiber through stiffness matrices and finite element meshes all the way up to actively controlled smart materials surviving inside a wind tunnel. By successfully evaluating, designing, and simulating these anisotropic materials based on strict strength and stiffness criteria, engineers are unlocking a totally new era of design. Which leaves us with one incredibly exciting question to ponder. As we perfect the simulation of these smart composites, what impossible structures are we going to build next? Thank you so much for joining me on this explainer, and keep exploring.